So that used torsion. Einstein used torsion. So
what is torsion?
it's the torquing of space-time itself.
The torquing of space-time.
So general relativity and that gravitation, which is curvature. So so Élie Cartan, a mathematician, wait a second, from the old mathematics from the 1800s, there should be something to twist space-time as well. He introduced this space-time torsion. That's even crazier than torsion. Torsion is already so crazy that...
Here we go. I'm going to start it off today for you guys. Spitting some bars. All right. Anthony makes videos. Here we go. Another master got me talking. Don't with hawking. I'm speed running while you're walking. You're skimming papers. My math game's getting even harder. Now I'm a monster. Read a concept, now I got it. Philosophizing, it's no problem. Top it, you cannot top this. You've got more L's than a hard list. As for my contents, another section, now I promise. Curvosculating, no debating. Your channel is all about no masturbating. What the f***? That's enough of that. Okay. I don't know if I'm even going to keep that in, but here we go. Another differential geometry stream for you guys. And today we're going to be talking about where I left off last time. So we're going to be talking about the principal normal, the osculating circle, curvature, torsion, the binormal, moving trihedron of a curve. Actually, it's not moving. No, it is moving. So let's just get right into it. Section 12, principal normal, curvature, and osculating circle. We will now introduce the important concept of the curvature of a curve. Let a curve C be given by an allowable parametric representation of the vector x in terms of s, that is to say the arc length, instead of a parameter t, which is just like an interval on the real number line bounded by a and b, possibly open, possibly closed on the endpoints. But this parametric representation in terms of the arc length is of class r greater than or equal to 2. That is to say, it is at least twice differentiable. Differentiating the relationship, which is the scalar product or the dot product of the tangent vector t with itself, that is to say t dot t equals 1. Differentiating this, we obtain t scalar product with the first derivative of the tangent vector t in terms of arc length. Notation-wise in this book, when they use the dot notation for derivatives, then it's going to be a derivative in terms of arc length, whereas if it uses the prime notation, that's a derivative in terms of just a normal parameter t. Normal, not... Anyways. Hence, if the vector t dot equals x double dot, or the first derivative of the tangent vector t is equal to the second derivative of the parametric representation of the curve x, if this vector is not the null vector, it is orthogonal to the unit tangent vector t and consequently lies in the normal plane to C, capital C, the curve that is, at the point under consideration. The first derivative of t, the tangent vector, also lies in the osculating plane, which I went over a few episodes ago. The unit vector p of s, which is equal to the first derivative of the unit tangent, or of the tangent vector, in terms of arc length, the first derivative over its magnitude or its length, not absolute value, t dot of s. So we take the tangent vector, divide it by its length or its magnitude, which has the direction and sense of the first derivative of t, is called the unit principal normal vector to the curve C at the point of the x vector evaluated at a particular value of arc length s. The straight line passing through this point and containing the unit principal normal, is called the principal normal to the curve C, capital C, at this point. Since the first derivative t lies in the corresponding osculating plane as well as in the normal plane, the principal normal is the intersection of these planes. And there's a picture that's going to come up in a page or two that's going to clear up a lot of this if you're having trouble visualizing it. The absolute value of the vector t dot, or the magnitude or the length, right? Kappa of s is equal to the magnitude of the first derivative of the vector t at s is equal to the square root of the dot product of the second derivative of the parametric representation of the curve x in terms of s with itself. That is to say, you take the derivative twice of the parametric representation x, take the dot product of that with itself, and then square root the result. And kappa here is greater than or equal to 0. This kappa is called the curvature of the circle, is called the curvature of the curve capital C at the point of the vector x evaluated at s. The reciprocal of the curvature, which is rho of s, is equal to obviously 1 over kappa of s, where kappa is greater than 0, is called the radius of curvature of the curve C at the point vector x evaluated at s. Straight lines are the only curves whose curvature vanishes identically, because from kappa equivalent to 0, we obtain that the vector x at s is equal to the vector a times scalar s plus the vector c, where the vector a is a constant unit vector and the vector c is also a constant vector. It will be advantageous for our later considerations to use a special letter for the vector t dot. We set k of s equal to t dot of s. So just a little bit notation, because it's going to get a little bit intensive here in these next couple sections, but it's not really that bad. So this k of s vector is called the curvature vector of the curve C. We now mention the following fact. While the sense of the unit tangent vector to a curve depends on the orientation of the curve resulting from the choice of a certain parametric representation, the unit principal normal vector is independent of the orientation of the curve. Its sense does not change if the parameter s is replaced by the parameter s star equals negative s, or any other allowable parameter. That is to say, any allowable parametric representation that you can have for your curve, the curvature and radius of curvature are going to be invariant. Moving along, the point M on the positive ray of the principal normal at a distance rho of s from the corresponding point P of the curve C is called the center of curvature. The circle in the osculating plane whose radius is rho and whose center is M is called the osculating circle of curvature of capital C at the point P. Obviously, the osculating circle passes through this point P. The tangents to the curve C and to the osculating circle at P coincide. And this will be considered in a later section where we talk about contact, and the osculating sphere. So this is the osculating circle right now, but in about 7 sections, it's going to be generalized to an osculating sphere. From the definition of M, it follows that the position vector of this curvature, radius of curvature here we've got, z, is of the form z equals vector x plus scalar rho times vector p, which is equal to vector x plus rho squared times t dot, the first derivative of the tangent vector in terms of arc length, where kappa is greater than 0. We will now derive from, what's 12.3? It is the equation for curvature. So kappa of s is equal to the magnitude of the length of the first derivative of the tangent vector. Using that, we can derive an analytic expression of the curvature, which is valid when the curve C is represented by any allowable parametric representation, the vector x in terms of t, okay, instead of s, the arc length now, we're switching back to t, of class r greater than or equal to 2. So it's twice differentiable. I'm going to read that one more time. Using the equation for curvature, kappa, we will now derive an analytic expression of the curvature, which is valid when the curve C is represented by an allowable parametric representation x of t. It's a very subtle distinction here between t and arc length, and this is going to come into really big importance in the next two sections. In consequence of the equation for the unit principal normal by the equation of curvature on the previous page is equivalent to t dot equals kappa times vector p, where p is the unit principal normal. Taking the vector product of both sides of this equation by t, we find that the vector t cross product with the first derivative of t with respect to s still is equal to the first derivative of x cross product with the second derivative of x, still in terms of arc length, which is equal to the tangent vector t cross product with the scalar kappa times the unit principal normal vector. Since the tangent and unit principal normal vectors are orthogonal unit vectors, then using the definition for cross product, where if we have vector v, which is equal to the result of taking the cross product of vectors a and b, then the magnitude of that result of the cross product, v, is equal to the magnitude of a times the magnitude of b times the sine of the angle between a and b. So, using this, we obtain kappa is equal to the magnitude of the first derivative of x in terms of arc length, cross product with the second derivative of x in terms of arc length, which, if we change that from terms of arc length to terms of another parametric, another parameter t, then we have the first derivative of x, x prime, cross product with the second derivative of x, x double prime. So these are both in terms of t now instead of arc length x, s. If we have the magnitude of this cross product, we multiply that by the square of dt ds. So once again, the magnitude of the first derivative of x cross product with the second derivative of x, where these are in terms of arc length. If we move this to another parameter t, then we just have to multiply by the second derivative of t with respect to s. Hence, by means of 9.7, which is a transformation in infinitesimal terms on arc length, so ds squared is equal to the sum from I equals 1 to 3 of dx sub I squared is equal to dx dot dx. It's just a transformation of infinitesimal arc length to another infinitesimal parameter. We obtain another version for the expression for curvature, kappa, which is equal to the magnitude of x prime crossed with x double prime all over the magnitude of x prime itself squared, which in consequence of 5.11 here, which is actually the identity of Lagrange, which is just what do you get when you take four vectors, you cross product two of them each together, and then the results of each of those, you dot product those together. Simple formula that you probably learned in, I don't know, Algebra 2 or trigonometry, or you never learned it and you just learned it now, or you forgot it and you were just reminded of it now. In consequence of this, then we can rewrite the expression for curvature that we just obtained in terms of t as, in the numerator, we have the entire quantity which is being taken a square root of, which is x prime dot x prime times x double prime times x double prime. These two things multiplied together minus x prime times x double prime itself squared. This entire quantity, you then take the square root. This is over the denominator of the quantity x prime dot x prime, and I believe that is a, what is that? I can't even read. I think it's 2/3. I can't even read that on here. We're going to open up the book and see what that number is, because it's literally blurred on the PDF here. And it looks pretty blurred in here, but I think it actually says 3/2 because I'm not actually going to, there's just a disgusting amount of algebra to follow along with. If you want to do all this stuff for the next 3 sections here, sections 12, 13, and 14, you're going to have a lot of plugging and chugging to do. Okay, so, the denominator, we have x prime dot x prime, and the power, as I've been able to discern from squinting at the book, is 3/2. You're welcome. If in particular t equals s, then what we just obtained will, of course, reduce to the previously obtained expression for curvature in terms of arc length, which is what would make sense when you do a change of variables like this. So it's valid. Now we have this example here, which is kind of trivial, doing radius of curvature and curvature, but just of a circle that's lying in a plane. So we're going to skip that. We're going to revisit what I did in MATLAB at the end of last differential geometry stream. And I'm not going to plug it into MATLAB this time, but we have this example where we have the curvature of the circular helix, x of t equals first entry, r cosine t, second entry, r sine t, third entry, ct is constant. So the curvature of a circular helix is constant. By means of 12.7, which is our equation for curvature in terms of a parameter t, which is not arc length, we obtain that kappa equals r over the quantity r squared plus c squared. And this is a constant. If c tends to 0, because we know that it's a constant because it's not in terms of t, even though we have these floating values, or a floating value of c in here. So if c tends to 0, then rho, the radius of curvature, which is equal to 1 over kappa, tends to the radius r of the circle of intersection between the x1, x2 plane and the cylinder of revolution on which the helix lies. So if you remember at the end of the last differential geometry stream and I projected onto the x1 plane the unit circle or whatever you want to call it, that radius of the circle is the radius of curvature of that entire curve of the circular helix. So we have a couple problems here. We're going to skip problem 12.1 and we're going to go to 12.2, which is fairly interesting, but it's a quick one. Prove that the locus of the centers of curvature of a circular helix C is a circular helix C star. Determine a circular helix C for which the cylinder of C star coincides with that of C. So it's just kind of a little cool problem where when you actually find the representation of the curvature of the curve you're working with, you obtain the same curve back. I'm going to zoom to the end. Oop, almost. All right. So in a previous problem in chapter 9 or section 9 here, which was specifically about arc length, I skipped over it in the speed run, but and you can kind of tell by some of the stuff that I already went through about like the infinitesimal change of variables between an infinitesimal arc length versus infinitesimal of your original parameter t. Skipped that in the speed run, but there was a problem in there where they took our beloved circular helix and changed it from being in terms of t to terms of s, the arc length. So that's just what the first little bit of this is saying. We set w squared equal to r squared plus c squared merely for ease of being able to write this and have it all displayed on this page. And we have s equal to w times t, so that's the specific way we're going to be changing variables here. So therefore, the vector x in terms of s, which represents the circular helix, is first entry r times the cosine of s over w, second entry r times the sine of s over w, and the third entry is c times s over w. Now, subsequently to this, we easily obtain the second derivative of x in terms of arc length s, which is the first entry being negative r over w squared times cosine t, The second entry is negative r over w squared times sine of t, and the third entry is 0. So by the equation for the radius of curvature, or curvature, since they're both reciprocals, that we just went over, rho is equal to w squared over r. So we thus have from 12.6, and what is 12.6? Oh, it's the vector for the actual radius of curvature itself. So not radius as in the length of it, but it's what is the actual vector of like the radius of the osculating circle. Okay, z is equal to x plus rho squared times x double dot. So since we just calculated x double dot, we have for the first entry negative c squared over r times cosine t, and then we have for the second entry negative c squared over r times sine t, and the third entry we have ct. This is a representation of a circular helix on a cylinder z star of radius c squared over r. So how do you get the circular helix, whereas curvature is the helix itself? Well, if c equals r, then z star coincides with the cylinder z on which the given helix lies. If c is greater than r as well, then z star is exterior to z, and if c is less than r, then z star is interior to z. So that's a nice little warm up. Now we can go all the way back. Oh, almost. Trying not to overshoot it so that this isn't too long. Okay, so now we're in section 13. Binormal and the moving trihedron of a curve. Not a tetrahedron, not a dodecahedron, not a cube. This is a trihedron. We're not going to get into a rant about Platonic solids and Pythagoras and Timaeus and all that. We again consider an arbitrary curve, capital C, given an allowable representation, vector x of s in terms of arc length, once again, of class r greater than or equal to 2, that is to say twice differentiable at least, where s denotes the arc length of the curve capital C. To every point of the curve at which kappa is greater than 0, so the curvature is positive, we have associated two unit vectors. The unit tangent vector t of s, which is equal to the first derivative of x dot of s, and the unit principal normal vector p of s, which is equal to t dot of s over the magnitude of t dot of s, which is equal to rho of s times x double dot of s, where rho, once again, is the radius of curvature, and x double dot of s is the second derivative of the parametric representation of your curve capital C in terms of arc length s. Kappa is greater than 0. We have positive curvature. And non-zero. It's not kappa greater than equal to 0. It's just kappa greater than 0. These two vectors are orthogonal. So the tangent vector and the unit principal normal vector are orthogonal to each other. We now introduce a unit vector b of s, which is equal to the cross product t of s and the unit principal normal s. Oh, camera death. Here, let me back up. We now introduce a unit vector, b of s equals t of s cross p of s, which is orthogonal to t and p and is called the unit binormal vector of the curve capital C at the point vector x evaluated at a particular value of s. The orthogonality is an immediate consequence of the definition of the vector product, which we see in the preliminaries. From this definition, we also see that the vectors t, p, b in this order, so move your right hand in the direction of t and then sweep it into the direction of p, and your thumb is in the direction of b. Because t, p, and b in this order have the right-handed sense. So the fact that b is a unit vector can be seen from, okay, we can go back to the preliminaries and verify this. And it's that whole a cross b is equal to magnitude of a, magnitude of b times sine of the angle between them to get the magnitude of your result. Anyways, to every point of a curve at which the curvature is greater than 0, kappa greater than 0, but is not 0, we have now associated three orthogonal unit vectors. Wow, look at that geometric structure that we've been building up on the curves that we're investigating. Isn't that something? The triple TPB is called the moving trihedron of the curve. And we're going to see a picture of this a little bit later. For several investigations, it is convenient to use the Cartesian coordinate system whose axes are the straight lines passing through a point of the curve in the direction of the corresponding vectors t, p, and b respectively. The motion of the trihedron along the curve will be considered in a subsequent section, which I don't think I'm going to do today. The straight line passing through a point vector x of s, so the vector x is evaluated at a point s, of a curve capital C in the direction of the corresponding unit binormal vector b of s is called the binormal to C at the point x of s. The vectors t and p span the osculating plane s of the curve. And now that I'm on this page, you can just take a second to appreciate the picture in figure 16. It really just simplifies all of this. And if you haven't realized, like, this whole theory of curves chapter and several other chapters here are really just building up terminology and notations. We could get into that, but we need to keep moving along. The vectors p and b span the normal plane n, and it is depicted very nicely here in figure 16 so that you can understand what's going on. The plane spanned by the vectors t and b is called the rectifying plane. So now we have an osculating plane, a normal plane, a rectifying plane, and if you're working with a plane curve, then I refer to that as a plane. So, since t, p, and b are the normal vectors to the normal, the rectifying and the osculating plane, respectively, we have the following representations. A, the normal plane is, you take the vector z, which corresponds to the radius of curvature, and then you add the vector x, but in the opposite direction. Or you could say you take z minus x, and the result of that, you then take the dot product with the tangent vector t. So another way to say this is z minus x, and then dot t. And then you take that result and you set it equal to 0. That is your equation for the normal plane. We did something like that 2 episodes ago in the osculating plane differential geometry stream. Correspondingly, we have the rectifying plane, which is z minus x dot with p equal to 0. We need to have positive non-zero curvature. And the osculating plane, z minus x dot with b equal to 0, still with positive non-zero curvature. So we have equations for a normal, rectifying, and osculating plane. And indeed, earlier in the osculating plane section where you have the determinant of, in the first column, z minus x, the second column you have x prime, and the third column you have x double prime, you can obtain that from these equations here. Moving right along. We have a trivial problem here that I'm not going to do, which is if you have two twisted curves which are in a one-to-one correspondence, then corresponding points of the tangents are parallel, and the corresponding principal normals and binormals are also parallel. So we can skip that. And now we are into torsion.
Okay, this is an example of what torsion looks like?
Yeah, I mean, torsion is somewhat of a general term as well, so it gets used in other applications as well. So that's why I like to use the term space-time torsion just to point out. But yeah, exactly.
Space-time torsion.
So you can imagine that.
Torsion. Everybody wants to talk about torsion. In fact, I'm going to zoom over here. We have Einstein-Cartan theory here, which it just says is a classical theory of gravitation similar to general relativity, proposed by Élie Cartan in 1922. This guy, Élie Cartan, he's pretty cool, but I like his son a little bit more, Henri Cartan. Henri Cartan, him and his buddies started this group that they called the Bourbaki group, and basically they would publish these science texts under the pseudonym Nicholas Bourbaki because they were in the 1940s or something like that, 1950s. And so after World War II, they felt that there was a generation of mathematicians and scientists that had been lost due to the war. In fact, one of the guys who was closely related to all this, had his freaking mouth and nose blown off during the war. You know what I'm saying? Brutal. And so Élie Carton's son, Henri Carton, wrote this awesome book about complex variables, which I have over on my shelf in the original French, okay? That's another thing. A lot of this theory of curves stuff, it was done by French people. And unsurprisingly, is it because maybe in like the 1600s, like in last episode where I was talking about Fermat and Descartes going back and forth. Okay, they're French guys. Well, they didn't have Google Translate back then. Translating is really expensive. There's not a lot of translators because you need to have been able to travel between these different places. And there weren't such things as, state required education where everyone is being forced, a particular dialect or received pronunciation of whatever language. So for hundreds of years leading up, the theory of curves was pretty much dominated by French mathematicians in my estimation. Anyways, we're going back to this quantum gravity stuff, and we say, ooh, Einstein-Cartan theory. I wonder what that's all about. I want to learn about it. Well, if you just look up how many times torsion is used in this Wikipedia page, we've got 48, okay? So we're not even gonna read this Wikipedia page because it's like, what is even torsion? I haven't even talked about that. But I'm gonna have more historical stuff to say in just a moment. Don't wait, okay? Anyways, so we consider an arbitrary twisted curve which has a parametric representation x of s, so this is not evaluated at a particular value, of class r greater than or equal to 3. That is to say, it is at least 3 times differentiable with an arc length s as a parameter, as I just said. The curvature, represented by kappa of s, as we just went over, measures the rate of change of the tangent when moving along the curve. It measures, so to speak, the deviation of the curve from a straight line in the neighborhood of any of its points. The torsion to be introduced now should, roughly speaking, measure the magnitude and sense of deviation of a curve from the osculating plane in the neighborhood of the corresponding point of the curve, or, in other words, the rate of change of the osculating plane. Interesting. Torsion is the rate of change of the osculating plane. Wonderful. We assume that the curvature is positive and non-zero at this point. Since the osculating plane is spanned by the unit tangent vector t and by the unit principal normal vector p, the unit binormal vector b is the normal vector to this plane, which we just went over. In the case of a plane curve in the osculating planes, the osculating planes coincide with the plane of the curve, the plane. Then b of s is a constant vector, and we have b dot equals 0. So the first derivative of b in terms of arc length s is equal to 0. It is therefore natural to consider the vector b dot in our present investigation. Differentiating the scalar products b dot b equals 1 and b dot t equals 0 with respect to the arc length s, we obtain b dot, the first derivative of b, so b dot b dot, that's weird to say. That's this whole fly dot notation is kind of weird. And the first derivative of b dot with t plus b dot with the first derivative of t equals 0. So since the first derivative of t dot equals kappa times p, the principal normal vector, we find from this relation that the first derivative of b dot with t is equal to negative b dot with the first derivative of t, which is equal to negative kappa times b dot p equals 0. It's a little bit confusing. I'm going to read it one more time. If we have the binormal vector, we take the first derivative and then we take the dot product of that with the tangent vector. This is equal to the opposite sense of the binormal vector, dot product with the first derivative of the tangent vector, which is equal to the negative curvature times the binormal vector dot product with the unit principal normal vector. All of these three relations are equal to 0. Hence, if the vector, which is the first derivative of the binormal vector with respect to s, is not the null vector, it is orthogonal to the vectors t and b and consequently lies in the principal normal. We may set this first derivative of the binormal vector B in terms of S equal to negative tau of S times the unit principal normal P of S, where we have positive non-zero curvature. And so scalar multiplication of this relation, this first derivative of the binormal vector in terms of arc length, by the unit principal normal, then we yield this tau of S, okay? Tau of S is equal to the negative unit principal normal vector in terms of S dot product with the first derivative of the binormal vector in terms of S. This tau of S that we just obtained is called the torsion of the curve capital C at the point x of S. That is to say, we're evaluating the parametric representation of capital C, the curve, at a particular value of S. We obtain this torsion, okay? The sign of the torsion has a geometric significance. It has been chosen so that the right-handed curves... Oh, there goes my battery. Goodbye. Okay, so the sign of the torsion has a geometric significance. It has been chosen so that the right-handed curves, for example, right-handed helices, that is helices for which in our previous beloved example, we have chosen C equal to H bar equal to 1, that is positive 1, have a positive torsion, tau of S, as will be seen in what follows. Now, an important historical note. Like I said, I was going to give another historical tangent. And that's something that I actually have come to appreciate about this book, is that it gives a lot of these historical little insights here. And I really appreciate it. So the name torsion was first used by what says here, Louis de Vallée in 1825. Now, I did a little bit of reading, and this is in error in the book. There is no Louis de Vallée. The real name of this guy is Louis-Léger Vallée. And he came up with all this stuff in a book that he published in 1825, indeed, so at least it got that right. But it was called Traité de la Géométrie Descriptive. And this guy, Louis-Léger Vallée, we stand on your shoulders, man. Merci beaucoup, monsieur. Nous nous tenons debout vos épaules, okay? This guy started off in the, what's it called? The Department of Roads and Bridges, I guess you could say. He was an ingénieur des ponts et chaussées. And he, went to school like anybody else, and then he went straight into working at the French Department of Roads and Bridges. And he rose all the way to the top to be the Inspector General. So he went all the way from being élève ingénieur, a student engineer, all the way to being the Inspector General. And along the way, he wrote the Traité de la Géométrie Descriptive. And that is where we get torsion from. That then later we have this guy, Louis Cartan, who comes along and he says, this might be really helpful. But as you can see, torsion is not like a super exotic concept. You could kind of imagine that like a guy who's designing roads and bridges, these concepts of like curvature, radius of curvature, torsion might be kind of useful for the engineering of roads and bridges, okay? So, and then you want to take these concepts and, transplant them now into physics, and everybody loses their minds. Seriously. But another thing about this guy, Louis-Léger Vallée, is that he does not have an English Wikipedia page. You can only find it in French. So, right? Here we go. French Wikipedia. Where you at, man? No respect on English side of Wikipedia, okay? And yeah, here we go. It's exactly like I just said. 1803 to 1806, élève ingénieur. Went all the way up by 1848, 1851, Inspector General. So I guess 1825, he was ingénieur en chef, chief engineer. Yeah, hell yeah, bro. You're a chief engineer, and he cranks out Traité de la géométrie descriptive. Merci beaucoup, monsieur. Bon fait. Well done. Anyways, sorry. Getting carried away here. Curvature and torsion are also known as first and second curvature, and a twisted curve is therefore called a curve of double curvature. We will not use these names, thank goodness, because that would be stupidly confusing. Let us now derive a representation of tau of s, torsion, in terms of the function x of s and its derivatives. So, inserting, 13.1, which is the equation of the unit binormal vector in terms of the cross product of the tangent vector t and the unit principal normal p, all in terms of arc length. So inserting that into the just received expression for torsion that we have up here, torsion of s is equal to negative p of s dot with the first derivative of b of s. We obtain tau is equal to negative p dot with the first derivative of b, which is equal to negative p dot with the derivative of the quantity of the first derivative of x cross product with the unit principal normal p, which is then equal to negative p dot product with the quantity of x double dot cross with p plus x dot cross with p dot. So I'm going to read that last one more time. We have negative p times the entire quantity, which has the first quantity, which is the second derivative of x, cross product with the unit principal normal, closed first quantity, plus second quantity, which is the first derivative of x, cross product with the first derivative of p, close second quantity, close the entire quantity. Now, p dot with the second derivative of x crossed with p is equal to, okay, that's why I said earlier the whole absolute value magnitude length thing is going to get a little bit confusing with the notation. This p dot with the second derivative of x crossed with p is equal to, this is a determinant. So it's the unit principal normal in the first column, the second derivative of x in the second column, and then the unit principal normal in the third column. This is equal to 0. So inserting the unit principal normal being equal to the radius of curvature times the second derivative of x, then by the equations for the unit principal normal, curvature, and radius of curvature that we just went over, we find that torsion tau is equal to the negative determinant of the first column being the radius of curvature times the second derivative of x, the second column being the first derivative of x, and the third column being the result of taking that's a derivative of the curvature times the second derivative of x plus the radius of curvature times, yikes, that looks like 3 dots, so the third derivative of x, which explains why on the previous page we made the requirement that we're working with the twisted curve that is at least 3 times differentiable. Moving right along, interchanging the first 2 columns and simplifying the last one, we have torsion equal to the curvature, the radius of curvature squared, times the determinant where the first, second, and third columns are the first, second, and third respective derivatives of x. Keep in mind still, this is all in terms of arc length still, because on the next page it's going to get hairy and we're going to transform it into the parameter t. So going back from arc length to our original parameter t. So in consequence of these equations for curvature and the radius of curvature, the expression that we just obtained is equivalent to torsion equal to, we have the numerator, which is the determinant where the first column is the first derivative of x, the second column is the second derivative of x, and the third column is the third derivative of x. Then this is all over the denominator of the dot product of the second derivative of x with itself. And now we're going to do a little bit of reasoning about the geometric significance of torsion. So get your mind ready for that. We pointed out in section 9 that the positive sense of curve corresponding to increasing values of s can be arbitrarily chosen. And I showed that in my MATLAB example last episode. One orientation can be changed into the other, for instance, by means of the transformation s equals negative s star. Under this transformation, the functions x dot and x triple dot are multiplied by a factor of -1, while x double dot remains unchanged. The right-hand side of 14.3, which is just our representation of torsion that we just got, instead of writing torsion in terms of a normal vector, tangent vector, binormal vector, we just want to have it all in terms of the a parametric representation in terms of the arc length that we were given, right? We don't want to have too many equations floating around ideally, even though we're going to have the right-hand side of the representation for torsion we just obtained that is only in terms of the parametric representation of x remains therefore unaffected by this transformation. We're changing the sense of it, okay? Or by any other allowable transformation which changes the orientation of the curve. Hence, the sign of the torsion must have a geometric significance. What is that significance, you might ask? Continuing on. Since x of s, the representation itself, we're not evaluating it necessarily at a particular value of s this time, is assumed to be of class r greater than or equal to 3, at least 3 times differentiable, we may write a Taylor series expansion of x perturbed by scalar h in the domain of arc length. The vector x at s perturbed in its domain by h. X at s plus h is equal to the truncated Taylor series expansion, which is the vector x at s unperturbed plus h times the first derivative of x in terms of s plus h squared over 2 factorial times the second derivative of x in terms of s plus h cubed over 3 factorial times the third derivative of x in terms of s plus Landau symbol h cubed, or little o of h cubed. That is to say, all of the terms of the expanded Taylor series that have in order of h cubed or greater. If we take all of those terms and we represent that by a function, let's call it f of z, and we have this other second function, g of z, which is equal to h cubed, then as that h goes to 0, then f of z over g of z goes to 0. That's just a reminder of what this little o Landau symbol notation means. So the vectors x dot and x double dot lie in the osculating plane. The vector over 6 times the third derivative of x in terms of s plus Landau symbol of h cubed will therefore determine the sense in which, in a neighborhood of the point the vector x evaluated at s now, the curve leaves the osculating plane. Because of continuity, the difference between this vector and the vector h cubed times x triple dot of s over 6 is arbitrarily small for sufficiently small values of h. The vector x triple dot of s will therefore also determine the aforementioned sense. The curve is right-handed if, at the point x of s that we're actually evaluating for a specific value of s now, for increasing values of s, it leaves the osculating plane to the positive side of this plane, which is determined by the sense of the unit binormal vector b of s. In this case, the angle between the vectors x triple dot and b, which is equal to x dot crossed with the unit principal normal vector, which is equal to x dot crossed with the radius of curvature times the second derivative of x double dot, must be smaller than 1/2 pi. Since the radius of curvature is greater than 0 and is non-zero, the same must be true for the angle between the vectors x triple dot and x dot crossed with x double dot. Hence, the determinant, which has in the first column x dot, in the second column x double dot, and x triple dot in the third column, is greater than 0. And in consequence of the equation for torsion in terms of arc length via the curve vector x, we must also have that the torsion is positive. That is, right-handed curves have positive torsion. So that whole entire paragraph is just to say everything about the handedness of curves and positive torsion. Right-handedness is associated with positive torsion. So it's kind of as you would expect, right? I mean, these are just conventions. You could switch it, but we're not going to do that. So right-handed curves, positive torsion. If it's not right-handed, negative torsion. Anyways, the reciprocal of torsion, which is sigma equal to 1 over tau, where tau is non-zero, is called the radius of torsion. Quick recap, in the beginning of this, we introduced curvature and the radius of curvature. So radius of curvature is the reciprocal of curvature. Now we introduce torsion, and the reciprocal of it is also correspondingly the radius of torsion. Pretty straightforward. And here's where it gets a little bit hairy when we're going to go from x in terms of arc length s, and we're going to go back to an original parameter, quote unquote, t. So imposing on x of s an allowable transformation of class r greater than or equal to 3, we obtain tau equal to, in the numerator, a determinant where the first column is x prime, the second column is x double prime, and the third column is x triple prime. These are all derivatives of your representation of the curve x in terms of t now, because we're using prime, not dots, in order to denote our derivatives. The denominator is the dot product of two quantities, the first quantity being x prime crossed with x double prime, and that's also the second quantity. What do you know? So that whole thing, you can reduce it to having a determinant where the columns are the first, second, and third derivatives in terms of t of our parametric representation of the curve capital C, which is a vector x. The denominator is then x prime dotted with itself. Take that and then multiply that by x double prime dotted with itself. Multiply those together, and now we subtract from that the quantity x prime dotted with x double prime. Take that squared. And this all goes without saying that the curvature is positive and non-zero. And you can prove this in a problem on the next page, but it's just, like I said, plugging and chugging algebra out the yin-yang. I don't have time to do this. I don't care about that. It's like I said, if you've got the equation, you might as well run with it. I don't need to practice algebra. Famous last words. I don't know. We now mention the following simple but important fact. A curve with non-vanishing curvature is plane if and only if its torsion vanishes identically. That is to say, if your torsion vanishes, you've got a plane. You've got a plane curve and a plane. And there's a proof which is really simple, and I'm going to admit it. So we're going back to our beloved circular helix problem, and we're representing it in terms of an original parameter t instead of arc length s. The circular helix vector x of t, which is equal to the first entry being r cosine t, second entry r sine t, third entry c of t, is right-handed if c is positive, greater than 0, and left-handed if c is less than 0, negative. And we have some pictures of this, which it's easier to just look at figure 17 than cranking it all out in MATLAB again. Even though that really was like the easiest, most baby example for MATLAB last time, if I'm being perfectly honest, just graphing stuff. Are you kidding me? Anyways, the curvature of this curve is given by the expression kappa equal to r over the quantity r squared plus c squared, which we got in the problem that we did in section 12. Since the dot product of the first derivative of x with itself is equal to r squared plus c squared, and the dot product of the second derivative of this x with itself is r squared, and the dot product of the first derivative of x and the second derivative of x is 0, we obtain from the atrocious representation of torsion in terms of the original parameter t. It's not that bad, but it's a little bad. We obtain from this that the torsion is equal to a scalar, which is 1 over r squared times the quantity r squared plus c squared. And this is all times the determinant, where in the first column we have negative r sine t, negative r cosine t, and r sine t. In the second column we have r cosine t, negative r sine t, and then negative r cosine t. Easy trig derivatives. And the third column is c, 0, and 0. This simplifies down to c over r squared plus c squared for the torsion of our circular helix. Then if this curve is right-handed, that is to say c is positive, then torsion is positive. And if it is left-handed, then we also have negative torsion. Very straightforward. The problems here we can skip over, and I think this video is pretty long already, so we're going to kick back off with the formulae of Frenet in the next one. The formulas of Frenet. Formulas of Frenet if you're a bête américain. See you guys in the next one.